An entity relationship, or ER diagram, is a visual tool that helps us represent how data is structured and connected in a database. It uses entities, attributes, and relationships to show the big picture. When building a database, we usually move through 3 stages: the conceptual model, the logical model, and the physical model. The conceptual model is the simplest stage of database design. It focuses on identifying the main entities in a system and showing how they relate to one another, without going into technical details such as keys or data types. For example, in a food ordering system, the main entities are customer, order, and food item. The relationships are straightforward. A customer can place many orders, and each order can contain many food items. At this stage, the goal is to understand the big picture of the system. The next stage is the logical model, which builds on the conceptual model by adding more detail. In the logical model, we define the attributes of each entity, assign primary keys, and identify foreign keys. For example, the customer entity will include attributes such as customer ID, full name, email, and phone number. Where customer is an entity, customer ID, full name, email, and phone number are attributes, and PK is a primary key. The order entity will include order ID, order date, and customer ID as a foreign key that links back to customer. The food item entity will include food ID, item name, and price. To handle the many-to-many relationship between orders and food items, we create a new table called Order Details, which includes order ID, food ID, and quantity attributes. Normalization in the logical model. The logical model also goes through a process called normalization, which helps us reduce redundancy and keep the data consistent. Let's use our food ordering system as an example. In unnormalized form, UNF, we had all customer information, order details, and multiple food items squeezed into one row. This caused problems like repeating customer data and multiple values inside a single field. In first normal form, 1NF, we expanded those multi-valued fields into separate rows. Now, each row holds just one food item per order, but we still see a lot of repeated information, such as Alice's details appearing multiple times. In second normal form, 2NF, we broke the data into 3 tables: customers, orders, and order details. Customers hold unique customer info. Orders link each order to a customer, and order details break down which food items are in each order. This removes partial dependency because non-key attributes such as full name, phone, and email now depend on the whole primary key customer ID instead of just part of it. In third normal form, 3NF, we noticed another issue. Food price was stored in the order details table, but price really depends only on the food itself, not the order. This is a transitive dependency. To fix it, we created a food item table where each food item and its price are stored only once. Order details now only references the food by its food ID. By the end of 3NF, our design is clean, efficient, and avoids duplication. Customers are stored once, orders are tracked properly, and food prices are maintained in a single place. The physical model is the final stage, where we implement the design in an actual database system, such as SQL Server, MySQL, or PostgreSQL. Here, we define the tables, assign data types to each column, and set up constraints like primary keys and foreign keys. For example, the customer table would use customer ID as an integer primary key, full name as a text field, email as a unique text field, and phone number as a string. The order table would include order ID, order date, and customer ID as a foreign key. The food item table would have food ID, item name, and price. Finally, the order details table would link orders to food items using order ID and food ID as foreign keys. Order ID and food ID together form a composite primary key, along with a quantity field. In summary, the conceptual model shows us the big picture, The logical model adds structure and enforces normalization, and the physical model translates everything into real database tables. Following these steps ensures that our database is well organized, free from redundancy, and efficient to use.